Hello everyone. In this video and in this new series, we will start talking about hypothesis testing. Now, I would like to remind you that statistics, or I should say the goal, the objective of statistics is to make inferences, is to infer about the unknown population parameters based on the sample data that you have, based on the information contained in that sample data. And those inferences, let me just move that dot over here. So we have a big population which can be parameterized, which can be explained using different parameters like the mean, the standard deviation, and so on. So what we do is, because we have no access to this, well, at least in totality, we don't have access to that big population, what we do is we draw samples from that. We can easily calculate the mean, the standard deviation, you name it, different statistics on that sample, and then analyzing the information contained in that sample, we try to make inferences about the big population. When we say population, it's not population of humans, but the big data set that we have. I think that makes sense. There are basically two different ways you can make inferences. One is estimating estimates of those parameters, of those population parameters. It can be interval estimates, point estimates, and so on. And secondly, you can you can test various hypotheses about those values, about those population values, basically. So, for instance, because we don't know what the population mean is, we can have a null or a hypothesis which says, well, everybody up to this day, they thought that the population mean is 10, but now I make this new suggestion that the population mean is not 10 or is greater than 10, for instance. So, and then we can try to test those new hypotheses. I hope that makes sense. All right, so now what I want to do is to talk about first the main components of statistical testing, hypothesis testing, and then we will look at different applications. So this is very important because we will lay the foundation for the key ideas of hypothesis testing. I'm assuming you guys all have taken a statistics course previously as an undergraduate student at least, but it might have been a while since that happened. So this is kind of like a brief summary of the very basics. So I will read along the text, and you guys can if you read faster, you can just skip some parts of this video. All right, so here we go. So many times the objective of by the way, the source for this is Wackerle. Before I forget, Wackerle, which is, I think it's the 6th edition that I have, or 6th or 7th, I don't remember, 6th edition book called by Wackerle. This is the author, Mathematical Statistics. Because our course is a mathematics course, it makes more sense to approach statistics in a rigorous way with a mathematical language. So the mathematical language gives us some precision about how to interpret the numbers in statistics. So here we go. So many times the objective of a statistical test is to test a hypothesis concerning the values of one or more population parameters. We generally have a theory, a research hypothesis, about the parameters that we wish to support. For example, okay, so this example turns out to be the main example that we will be working on, and we will be solving 4 examples related to this, 4 questions related to this example. Suppose that a political candidate, Jones, call him Jones, he claims that he will gain more than 50% of the votes in a city election and thereby emerge as the winner. That's his claim, Jones's claim. If we do not believe Jones's claim, we might seek to support the research hypothesis that Jones is not favored by more than 50% of the electorate. So Jones says that he will gain more than 50% of the votes, and we think he's not. We think that he will get less than 50% of the electorate vote. Support for this research hypothesis, also called the alternative hypothesis. So we come with an alternative hypothesis, right? The null hypothesis, is that Jones will have more than 50% of the vote, versus our alternative hypothesis is that that he will not, is obtained by showing that the converse of the alternative hypothesis, called the null hypothesis, is false. So we need to prove to the rest of the world that the null hypothesis, namely Jones's claim, right, that he will gain more than 50% of the votes, is false. That's what we want to find the evidence for. Thus, support for one theory is obtained by showing lack of support for its converse. So the way we will explain our point of view, the alternative hypothesis, is that we will refute the null hypothesis. We will falsify the null hypothesis. It's kind of a type of proof by contradiction. Because we seek support for the alternative hypothesis that Jones's claim is false, our alternative hypothesis is that P, the probability of selecting a voter favoring Jones, is less than 0.5. All right, so P is the probability of selecting a voter favoring Jones. So if the null hypothesis is false and the alternative is true, then P must be less than 0.5. If we can show that the data support rejection of the null hypothesis is P is equal to 0.5, at least 0.5, the minimum value at least. The null hypothesis, you can construct it in different ways. One way is let the null hypothesis be P equals 0.5 versus the alternative hypothesis be P less than 0.5. Right, and that makes sense. An alternative way to do it would be null hypothesis is I guess greater than 0.5, but in our case what we focus on the minimum value needed for a plurality, which is 0.5, because my point of view is that he's not gonna get 50%. So that's what I want to prove. So so that's what I focus. My alternative hypothesis is P is less than 0.5. We have achieved our research objective. Although it is common to speak of testing a null hypothesis, the research objective usually is to show support for the alternative hypothesis if such support is warranted. How do we use that data to decide between the null hypothesis and the alternative hypothesis? Obviously sampling. Suppose that n is equal to 15 voters are randomly selected from the city, and y, the number of people favoring Jones, is recorded. So you see, the city is a large city. There's no way ahead of the election we can ask every single individual, right? It will be too costly. It's probably impossible. But what we can do is randomly pick 15 people from the street or from the shopping mall or whatever, and ask them their opinion, whether they favor Jones or not, and then record how many of them. The number of them favoring Jones is Y. So here is the question. If none of the sample favored Jones, so you ask those 15 people and none of them favor Jones, what would you conclude about Jones's claim? Do you think Jones's claim is right, like that he will get at least half of the vote? I doubt it, right? So we will see. If Jones is actually favored by more than 50% of the electorate, it is not impossible to observe Y equals 0 favoring Jones. If a sample of size n equals 15, but it is highly improbable. That's right. So it might as well be we went to a neighborhood and pulled the sample from people in that neighborhood who, in general, they don't support Jones. Maybe that might have been the situation. But still, and you pull a sample of size 15 and none of them favors Jones, then Jones being favored by at 50% of the electorate would be a very improbable situation. It is much more likely that we would observe Y equals 0 if the alternative hypothesis were true. Thus, we would reject the null hypothesis in favor of the alternative hypothesis. If we observe Y equals 1, again, analogous reasoning would lead us to the same conclusion. Why? Because you ask 15 people in the street, one of them said he favors Jones, 14 of them says they are against Jones. So how likely is that during the general election Jones will be elected? I mean, very unlikely again. So why should we at least like 3, 4, 5 so that we can give some chance to Jones, right? Any statistical test of hypotheses works in exactly the same way and is composed of the same essential elements. So what are the elements of a statistical test, a hypothesis test? First, we need to establish the null hypothesis, then the alternative hypothesis, which is the opposite statement. This is the hypothesis that we are supporting. So we are going to provide evidence for our hypothesis by trying to reject the null hypothesis. So this is the idea behind hypothesis testing. We will construct a test hypothesis, and based on that, we will be again constructing a rejection region. If the test statistic falls into that region, then we will be able to reject the null hypothesis in favor of the alternative hypothesis. For our example, the hypothesis to be tested, called the null hypothesis and denoted by H0, is P equals 0.5. The alternative hypothesis, denoted by HA, is a hypothesis to be accepted in case H0 is rejected. The alternative hypothesis usually is the hypothesis that we seek to support on the basis of the information contained in the sample. Thus, in our example, HA is this. Usually, the way we would represent this is the following. We would write H0 and HA, the alternate. Sometimes this is written as H1. So H0 and HA. H0 is P is equal to 0.5. This is the thing we are trying to reject. And our alternative hypothesis is this. 0 is less than 0.5, where P is the probability that any randomly selected person will be voting for Jones. All right, so this is the way we construct the first two elements of the hypothesis test. Next, we need to talk about the test statistics and the rejection region. So the functioning parts of a statistical test are the test statistics and associated rejection region. The test statistics is a function of the sample measurements on which the statistical decision will be based. So basically the sample that we draw from the population, right? The rejection region, which will henceforth be denoted by RR, the rejection region, specifies the values of the test statistics for which the null hypothesis is to be rejected in favor of the alternative hypothesis. If for a particular sample, the computed value of the test statistic falls in the rejection region RR, we reject the null hypothesis and accept the alternative hypothesis. Does that make sense? If the computed value of the test statistic falls into the rejection region, we will reject the null hypothesis in favor of the alternative hypothesis. If the value of the test statistics does not fall into the rejection region, we accept H0, or rather I should say we fail to reject the null hypothesis, right? So we don't have enough evidence to support the alternative hypothesis. As previously indicated for our example, small values of y would lead to, if y represent, in our example, the number of people in your sample that support Jones, then small values of y would lead to reject the null hypothesis. Therefore, one rejection region that we might want to consider is the set of all values of y less than or equal to 2. So for instance, we might tell ourselves, I'm going to ask 15 people their opinion, and once I get their opinion of those 15 random people, if I realize that either 0, 1, or 2 people, anything less than or equal to 2, if 0, 1, or 2 people say that they support Jones, and everybody else say that they support the other candidate or they don't support Jones, then I think I will be confident enough to say that I will be rejecting the null hypothesis, that I will think that it's very unlikely Jones will be elected. We will use the notation rejection region is this, or more simply RR is y equals less than or equal to 2 to denote the rejection region. Now let me repeat, y here is the test statistic, namely the number of people in the sample who support Jones. All right, that's our test statistic. The rejection region is for that test statistic to be small, like 2, for instance. If you sample 15 people and 5 of them say that they are supporting Jones, it's not that clear after all. we still believe that's not good news for Jones, but it's not enough to reject the null hypothesis. Our rejection region is y equals less than or equal to 2, for instance. But this might be too strong, and that's exactly what we will discuss next. Finding a good rejection region for a statistical test is an interesting problem that merits further attention. It's clear that small values of y, say y is less than or equal to k, are contradictory to the hypothesis, the null hypothesis that Jones will have at least 50% of the vote, but favorable to the alternative hypothesis, where Jones will have less than 50% of the vote, or any randomly selected individual will have less than 50% chance of voting for Jones. So we intuitively choose the rejection region as y, the set of y values, test statistic values, less than a certain number k, right? K can be 2. In our example, we choose y less than or equal to 2, right? But it can be 3 and so on. But as k becomes larger and larger, our hypothesis test will be less strong, and that's exactly what we want to talk about next. More generally, okay, well, first the question is, what value should we choose for k? More generally, we seek some objective criteria for deciding which values of k specifies a good rejection region of the form y less than or equal to k. So how do we choose the k? That's the thing. So we can't just randomly pick y equals 2 like we did in the example. For any fixed rejection region, two types of errors can be made in reaching a decision. We can decide in favor of the alternative hypothesis when actually the null hypothesis was still true. So we made in that occasion, we would say that we made a type 1 error. Or we can decide in favor of the null hypothesis while in fact the alternative was true. In that case, we would say that we've made a type 2 hypothesis, a type 2 error. So rejecting the null hypothesis while it was true is a type 1 error. So we always kind of give priority to the null hypothesis, right? And we want to make sure we avoid rejecting the null hypothesis, at least for the type 1 error, rejecting the null hypothesis while it was true, right? So, okay. So therefore, this is a summary. Type 1 error is made if H0 is rejected when H0 is actually true. The probability of a type 1 error is denoted by alpha. The value of alpha is called the level of the test. Okay. Type 2 error is made if H0 is accepted while actually the alternative was true. The probability of type 2 error is denoted by beta. All right. So in our example, so let's talk about our example. For John's political poll, making a type 1 error of rejecting the null hypothesis when in fact the null hypothesis is true means concluding that Jones will lose when in fact he's going to win. So for John's political poll, making a type 1 error of rejecting the null hypothesis, which was that Jones will get at least 50% of the vote, when in fact it was true, means concluding that Jones will lose when in fact he's going to win. In contrast, making a type 2 error means accepting the null hypothesis when actually p is less than 0.5 and concluding that Jones will win when in fact he will lose. All right. So for most real situations, incorrect decisions cost a lot of like it can cost money, prestige, time, or imply a loss. So therefore, alpha and beta, the probabilities of making these two types of errors, measure the risks associated with the two possible erroneous decisions that might result from a statistical test. As such, they provide a very practical way to measure the goodness of a test. All right, so we have an example next. So in example 1, we will quantify what we discussed about here, and we will go ahead and measure alpha basically. All right, so here we go. So example 1, for John's political poll, n equals 15, so the sample size was 15 voters were sampled, and we wish to test the null hypothesis that Jones will get at least 50% of the vote against the alternative, which is that he will get less than 50% of the vote. The test statistics is y, so we're going to use the number, the people who say that they will be favoring Jones, from among those sampled. All right, so that's our test statistic. Okay, so we calculate alpha. We would like to do that, right? Given the rejection region. Okay, so and let me provide you the rejection region. So based on this, this is kind of a strong condition, don't you think so? So if we are saying that we are going to reject the null hypothesis, if we observe that 2 or less people will be voting for Jones, basically. So this is a rather strong assumption in a sense. So as a result, we are expecting alpha to be extremely, I would say extremely small. Because even when you ask 15 people and 5 of them is telling you that they are not going to vote for Jones, it's already providing you pretty good evidence, I would say, right? But we are saying that 5, we don't want to use 5, but rather we want to use just 2. 2 is extremely strong results that it will give us. All right, so alpha here is like we said, the level of the test, and it is going to give us the probability of a type 1 error. That's what we want to calculate, and this is the or you can say the probability of reject H0 when it was actually true, when H0 is true. All right, so or an alternative way would be this: the probability that the value of the test statistic is in the rejection region. All right, when actually H0 is true. H0 is true. All right, and this number is basically the probability. Okay, so I keep adding new stuff onto that. The probability that the sample test statistic is less than or equal to 2 when p is 0.5. So if p were to be 0.5, what would have been the probability of observing this, that 2 or less people will be favoring Jones? It would have been very unlikely, I would say, right? I mean, p equals 0.5. It's with that probability we were expecting to have y significantly higher. Like in average we would expect 6, 7 or 8 people at least supporting Jones, right? So what we will do is, because this is a binomial random variable okay, so we have a binomial random variable with a sample size 15, and we have 2 choices, right? Success or fail, in the sense that success for Jones and fail well, okay, so success means people voting for Jones, and fail means people not favoring Jones. All right, so if n is equal to 15 and the p is 0.5, so what's the probability of such a thing happening? So let's calculate that probability. Let's continue the equal sign here. So alpha therefore is equal to, so this is just the binomial distribution, right? So you can use Excel binom this function, so which I'm going to do next. But basically what we want is, I'm just gonna write down the formula here, but I'm going to show it to you on Excel right after that. So really it is 15, either, actually let me do it in 2 steps. It's either going to be the probability of y is equal to 0, or the probability that y is equal to 1, or the probability that y is equal to 2. So that's what we want to calculate. We want to calculate the probability that y will be less than or equal to 2 when if p were equal to 0.5. Does that make sense? So this is equal to, okay, by the binomial distribution that we studied earlier, 15 choose 0 times 0.5 to the power 0, 0.5 to the power 15, or 15 choose one way, 0.5 to the power 1 times 0.5 success to the power 1, failure to the power 14, or 15 choose 2 people will say they favor Johns, and the rest 13 people, they say they are against him. So the good news is you just realize that when you multiply these two, because the exponents, you add the exponents because they have the same base. So in all these, we can 0.5 raised to the power 0 times 0.5 raised to the 15. When you multiply them, is 0.5 raised to the 15. The same thing here, 0.5 raised to the 15, and the same thing here, 0.5 raised to. So therefore, we will have, we can factor that out basically, 0.5 raised to the power 15. And what is left is 15 choose 0 plus 15 choose 1 plus 15 choose 2. That's it. And if you do all these calculations and round it to the nearest, I think this comes out like that, 0.004. So if we decide to go with the rejection region where y is less than or equal to 2, this thing, if we go with this rejection region with y less than or equal to 2, we subject ourselves to a very small risk of concluding that Jones will lose if in fact he's a winner. Does that make sense? Remember, alpha is the probability of a type 1 error. So we are saying that us having a type 1 error is this 0.0. So this is about what? 0.4%. It's very, very unlikely that we will make a type 1 error of rejecting the null hypothesis while it was true. All right, that makes sense. So let's make sure we understand this this whole thing one more time. So we are saying here that if the null hypothesis were true, us rejecting it, we would have only rejected it if it was on the rejection region, meaning y, the number of people supporting Johns in the sample were either 0 or 1 or 2, right? So what we did is we calculated those individual probabilities based on assuming that p was 0.5, and then we came up with this value for alpha, and that shows the probability that, or the probability that we will conclude that Johns will lose the election while in fact he's a winner, right? This shows the risk that we have an extremely small risk of making a mistake here. Okay, so we will just do the same thing. I'm supposing that you guys had a chance to look into that example. Now let's have a look at the same thing using Excel, okay? So what we decided to do is the following. So we will observe different values for y. It can be 0 or 1 or 2 or 3 actually. So if you sample 15 people, it can be anything from 0, the number of people who say they are supporting Johns will be anything from 0 to 15. And let's have a look at the individual probabilities of those happening. So we are going to use binom. Well, either we can use directly the formula, or we can use returns. Let me see, which one do we returns the smallest value? No, we want a probability actually, so this thing. Okay, so the number so the number is 0. The number of trials is 15 trials. The probability of success is 0.5. And is this a cumulative number? Oh, we could have done it this way too. Okay, so let me show it later on. Okay, and this is false. I'm gonna not choose. Oops, extremely small number. Do you guys see that? This is a scientific notation. So it tells you that the number is tiny, but I don't like scientific notation, to be honest. Let's just write it in normal way, because for most people the scientific notation is very confusing. Okay, and by the way, let's add some decimal places of accuracy here. Extremely tiny number. And basically what I will do next is just to drag it all the way down, and boom. So let's see if these numbers add up to 1. Yes, the sum is equal to 1. Okay, so what did we do here? The probability that if Johns were to be like the probability that if the probability of any randomly given person supporting Johns was 0.5 or above, at least 0.5, what is the likelihood that from among the 15 people that I ask, that I will have nobody supporting John's? It's impossible. I mean, it's almost impossible, I should say. How about 1 people? Again, extremely tiny. 2 people? Again, extremely tiny. So the question says, what's the probability that this number y is less than or equal to 2? Well, oops, how did I do that? Hold on. Less than or equal to 2. Okay, so that would be equal to, all we will do is just add the 3 numbers here, just sum the 3 numbers. So this is the sum of those 3 numbers. There you go. And obviously, if you were to round it, I think in my example, I went ahead and rounded it. So let me just go ahead and round it to only 3 decimal places. There you go. So when you round it, you get the same answer. Alternatively, we could have directly used the less than or equal to 2, the cumulative distribution function. So let me also show you that. Binom.dist, number of successes 2 or less, right? Out of 15, the probability of success for each individual trial is 0.5, and we want a cumulative. So that will give us 2 or less directly, basically. Does that make sense? Boom, the same answer. And again, what we can do is we can remove some of the, there you go. So either you come to this table and then you add up these numbers like we did in the first solution, or you can directly use binom this with a true cumulative. All right, but regardless, this supports the earlier result that we numerically did it using combinations, manually solved it. So if our rejection region is as strict as you will only reject the null hypothesis, like you will only reject believing Johns will be elected only if the from the sample you get extremely small number of people supporting Johns, and that's what we did here indeed. All right,